Now let's analyze the same problem from an energy perspective. We can solve this problem without ever resorting to the equations of motion simply by using what we know about energy. Now we start with the kinetic energy. Usually we use Ke0. For some reason here I decided to use Ke1 because I guess 1 and 2, we're going to have kinetic energy here and a kinetic energy here. And we're going to have a change in potential energy. Now, the kinetic energy here is easily found from 1/2 mv squared. If we assume that the ball has a mass capital M, it really doesn't matter what the mass of the ball is, so we're going to call it capital M. And we're going to get 112.5 meters per second squared times M. The change in potential energy, the ball is dropping, potential energy decreases. Remember, the potential energy comes when we lift the ball from here to here. We get a potential energy that's equal to the work that we did in lifting it from here to here, or the potential energy at least changes between this point and this point by that amount. So the change of potential energy when the ball drops is going to be the negative of that amount. When we lift the ball, we have to exert a force equal to mass times gravity, the mass of the ball times acceleration of gravity, and we do that through a distance of 20 meters. So there's a force times distance if we lift it. If it goes down, there's going to be a negative of that. So that our change in potential energy is negative mg times 20 meters, and g of course is your 9.8 meters per second squared, so we get negative m times 196 meters squared per second squared. And this is our change in potential energy. Now, as we found before, the velocity at this point was 25 meters per second. Let's go a little bit lower and see. We found that from the equations of motion. Okay? Now we're not actually, in this case, solving the problem using energy, I guess. We are just looking at the energy situation, and then we'll use what we discover here in solving other equations using energy. Okay, so we have a 25 meter per second velocity at this point, and that gives us a kinetic energy of 312.5 meters squared per second squared times big M. Now this is approximate, and I'm really using an inappropriate number of significant figures here. So forgive me and don't make the same mistake. In any case, we see what? The change in kinetic energy is from 112.5 meters per second squared times m to 312 meters squared per second squared times m. Well, from 112.5 to 312.5 is a change of 200. So our kinetic energy changes by 200 meters squared per second squared times m. Just this one minus this one. Our potential energy changes by negative 196 meters squared per second squared times m. Now, remembering that the number of significant figures is a little excessive, really this is the same as this. This is about 200, this is about 200. Or if you wish, this is about 196 and this is about 196. These are really equal. And we see that the kinetic energy change and the potential energy change are equal and opposite. Now that makes perfect sense if you think about it. What's happening here? You got some kinetic energy and a potential energy here. The potential energy decreases. That energy can't be lost by the conservation of energy. The energy got to go somewhere. Where does it go? Well, it gets pumped into the kinetic energy. The potential you lose is equal to the kinetic you gain. So we have a gain in kinetic that's equal to the loss in potential. And of course, as we've seen before, that tells us that the change in kinetic plus the change in potential equals 0. We can see that right here. They're equal and opposite. And that the change in potential energy is, of course, the negative of the work done by gravity, as we saw here. This holds any time that gravity is the only force acting on the object. If there are other forces, air resistance, dissipation of other types, friction, a jet engine attached to the object, this can change. But if it's falling only under the only under the influence of gravity, these two have to be in this relationship. The kinetic energy gain and the potential energy loss are equal.